I cover with one word. So it's a great pleasure to invite you to welcome you to the seminar today by Surjeet Rajendran. This is something that many of us would have been looking forward to hear about, and we're glad that Surjeet has made himself available and to talk about this exciting topic. So over to you for this new nonlinear quantum mechanics.
Yes, thank you very much for inviting me. I actually grew up in Chennai, so it's sort of amusing that I'm giving a talk at IIT, but I'm actually in upstate New York, where it's very cold. All right, so the talk I'm giving is on a causal framework for nonlinear quantum mechanics. And feel free to interrupt whenever you have a question. I mean, I won't quite be monitoring the Zoom directly, so just please speak out. All right. So the question one can ask is, why should we want to modify quantum mechanics? And really, the issue is this, right? If you think about quantum mechanics was a theory that was built on observations that people made in the early 1900s. Literally, a bunch of people got together in a conference, and they told us that these are the rules of quantum mechanics. So why should it be that a bunch of rules that people came together with in a conference should somehow be the absolute truth, right? We modify every other theory in physics, general relativity, standard model, whatever. How come we never want to modify quantum mechanics? Why should it somehow be the absolute truth? So if you want to modify quantum mechanics, you have to first ask, what are the sides of quantum mechanics that you want to ask? What aspects do you want to change? And I would say that there are really only just two postulates of quantum mechanics from which you can pretty much derive everything else about the theory. The first is that probability is a fundamental and essential aspect of describing nature. And the second is linearity of time evolution. Okay. Now, as you undoubtedly know, sociologically, it is the case in physics that when someone is trying to talk about modifying quantum mechanics, the usual jokes are that the person is either close to retirement or they've gone crazy. Okay, now I'm not exactly close to retirement, so maybe I'm crazy. But really, we should understand, why does this sociology exist? Why is it that we think it's a waste of time trying to modify quantum mechanics? And that is largely because the large number of people who have tried to modify quantum mechanics have generally tried to eliminate probability from quantum mechanics. Now, probability makes people uncomfortable, but it's a fundamental fact about the world. So it is not a surprise that if someone tried to come up with a theory that eliminated probability, that they would fail. And that is largely the reason why that field has more or less been discredited, because the work has gone nowhere. On the other hand, one can ask a somewhat different question. What if we accept probability as being fundamental to the world, but why should time evolution still be linear? In other words, could there be nonlinear time evolution in quantum mechanics while accepting probability as being a fundamental part of the world? Strangely, this aspect has not been explored very much, and that is exactly what we are trying to do. So before I go on to linearity, let me even spend a few minutes telling you why going after probability is a waste of time, why one cannot eliminate probability from quantum mechanics. So why is it that probability is a fundamental part of describing nature? So let us accept two facts about the world. If I, for example, take a finite system, like let's say the hydrogen atom, and let me pick some arbitrary energy, and let me ask, how many energy levels are there below that arbitrary energy? For a finite system, there are only a finite set of energies below some value that I choose, right? You have a discrete set of states, in other words, discrete set of energy levels. Let's accept that as a fact about the world. Okay, if you don't have that, you won't get sensible thermodynamics, etc. But for now, let's simply accept that as a fact about the world. The second fact about the world is that we have continuous observables and symmetries, right? Rotation, translation, things of this kind. Now, notice that these two facts are not going to play well if you decide that the theory of the world has to have complete determinism for every observable. In other words, if you decide that every observable has to be continuously known to you at all time and deterministic, I'm going to argue to you in a second that these two facts don't play well with that requirement. So to explain this, let me start by asking the simple question. Could an electron in an atom somehow have a well-defined position? Is that possible? So for example, right, when I was a child, the picture of the atom I had in my head was that the electron went around the proton in a circle, just like how the Earth goes around the sun. Why is that picture wrong? So suppose that picture was correct, right? So that we really had an energy level of the hydrogen atom, let us say, where the electron went around the proton. The electron has a well-defined energy and a well-defined position. Suppose such a quantum state actually existed. You could now apply a rotation, and because rotation is a continuous symmetry of the theory, you would get another state of the system, but the electron is now in a different location and has exactly the same energy as it did before. And since rotations are a continuous a continuous symmetry, you can basically start with a single state where the electron has a well-defined position and end up getting an infinite degeneracy where all of these states where the electron would be in well-defined positions but have the same energy as everything else before. And that, of course, contradicts your assumption or a fact about the world that the world only has a finite number of energies below any given energy level, right? So quantum mechanics fundamentally is a compromise between these three entities, if you will. You sacrifice absolute determinism. You sacrifice a requirement that every observable is known to you at all times with absolute certainty. And by sacrificing that absolute determinism, you're able to preserve the fact that the world has continuous symmetries and observables, and also the fact that we need to have a finite set of energy states, either as an observed fact about the world or if you want to have sensible thermodynamics. So this tells you very quickly why anyone who's been trying to come up with a way to eliminate probability completely from quantum mechanics will fail, because you're fighting against well-known facts about the world. Now, many of the theories or theorems, if you will, that tell you how quantum mechanics is distinct from classical mechanics, such as the Bell inequalities, the Koch-Specker theorems, and the so-called SSE theorems, these are fundamentally making use of this fact, okay? So for example, how do the Bell inequalities work? They will typically look at some set of angular momentum states of the hydrogen atom, let us say. Now we know there are only a finite number of angular momentum states. But of course, I can measure rotation along a very large number of possible angles, okay? So then you realize that, look, since I can make a huge number of measurements of rotation, but I only have a finite set of angular momentum states, of course, I'm going to come in conflict between quantum mechanics that requires a finite set of states versus classical mechanics, which has an infinite set of possible values angular momentum could take. So these are the aspects of quantum mechanics that we have tested very well and that we have that are essentially hard to modify. But what about linearity, the other aspect of quantum mechanics? Linearity is a statement that the wave function of quantum mechanics does not interact with itself, right? If I have a wave function, it doesn't interact with itself. So let's think about the most practical consequence of linearity, and that is something called the Lamb shift. So if you take the Lamb shift of hydrogen, if you compute the energy of the 2s and the 2p state of hydrogen, right? So this is the hydrogen atom, and I'm putting the 2s and the 2p state. So if I ignore this QED correction which is an interaction of the proton with the electron, the 2s and 2p levels of hydrogen are exactly degenerate, okay? And if you think about that, that's a little weird, right? If you thought the electron was going around the proton and it was in some kind of cloud, right? Like a 2s, that's the kind of picture you have in your head. There's some charge distribution of electron around it. If I thought about that classically, I would have thought, look, I have a 2s sphere and the 2p is some kind of dumbbell. And classically, we've all done this as problems in our undergraduate career. You would compute how there is an electrostatic self-energy of this 2s and the 2p level, where you would expect to get a shape-dependent contribution to the energy of the electrons, of the electron state, from the fact that the electron is some charge distribution, right? So the electron was talking to itself through, let's say, electromagnetism. You would have expected the 2s level of hydrogen to have a somewhat different energy than the 2p level. But that does not exist because the theory is linear. But it's not that there is some fundamental principle of physics that prevents you from knowing about the shape of the electron cloud. If I put a second electron next to this electron, that second electron is very sensitive to what the shape of the electron cloud is, right? Clearly, the 2s electron would shield the nuclear charge more than the 2p electron. So this electron very clearly is aware of the shape of this electron cloud. So it's a weird thing, right? Why should the electron itself not be sensitive to its shape, while a second electron can be sensitive to its shape and is sensitive to its shape? So there has not been much work done on this. There have been only a couple of papers, really, in the history of quantum mechanics. And the typical issue that one runs into in dealing with these things is issues of causality. And could you construct a causal nonlinear theory? And then you have to think about measurement, right? What happens when you make a measurement? And also quantum field theory. But at the end of the day, how does all this fit into QFT if I make this nonlinear? So let's start with causality, because that is the most identifiable problem that people ran into. And this is what Weinberg tried. So let's just play this game, right? Let me take the Schrodinger equation, I d psi dt is h psi. This is the linear Hamiltonian. And let me now simply add a trial nonlinear term, an epsilon psi squared plus psi star squared, the whole thing multiplying psi. Great. What goes wrong? If I only had one particle in the world, nothing goes wrong with this theory. You can think of epsilon as some small parameter. You can do perturbative analysis, etc. You'll get your usual eigenstates, everything else. There's nothing dramatic that goes wrong for a single particle system simply because I put a psi squared, psi star squared term in the equation of motion. You can verify this. But the key point is that the world has more than one particle. And specifically, once I have more than one particle, entanglement becomes a fundamental aspect of quantum mechanics. So for example, I can take an electron here on planet Earth, and I can take an electron in, let's say, Mars. Okay, so let's say the electron on Earth is at X, and the electron at Mars is at Y. And now we can imagine doing the following thing. Let me take the electron at X and apply some local operation on it. Okay, so I'm going to do something to it, measure it, or make it interact with something else. So essentially, I can take the electron at X and let me apply a local unitary operation on the electron at X. Now, if you have terms like psi squared and psi star squared, like what I wrote down, you will say, look, the entire Hamiltonian that governs both the electron on the Earth and the electron in Mars is this wave function plugged into this expression. And when I do that, if I have this complicated entangled state and I change what happens to X, I will be changing the coefficients Cij that sit in front of alpha I of X, right? That's what happens when I actually apply a unitary transformation on the electron at X on Earth. Now, if I have terms like psi star squared, etc., appearing in there, whenever I change the coefficients on X, I'm instantly changing the coefficients of Y as well, of whatever is happening on in Mars. Which means that by doing a local operation on Earth, I have instantly changed what's going on in Mars. And that means the theory is not causal. Okay, so this was the problem with Weinberg's modification. So Weinberg wrote this theory down. He didn't even realize that he had an acausal theory, and Joe Polchinski pointed that out. And that's basically what most people remember, except there's a second part to Polchinski's paper, but he actually talks about how it might be possible to actually have causal nonlinear theories in quantum mechanics. Okay, and in many ways, what we did was really generalize that concept and really understand what it actually meant. So let me spend a minute here telling you why you should actually not think that nonlinearity should not play well with causality, that it should actually be perfectly reasonable to have causal nonlinear quantum mechanics. So let's just think about linear quantum mechanics for a second, and let's think about the electron coupled to electromagnetism. Now, if I have an electron that wants to go from point A to point B, quantum mechanics tells you that the way the electron goes from point A to point B is via the path integral. It takes all possible paths to go from A to B. Now, the fact that quantum mechanics is linear is a statement that these different paths of the electron do not interact with each other via electromagnetism. Okay, you compute the Lagrangian, whatever it is, on the path, but the Coulomb electric field of this electron does not, of this path, does not talk to the Coulomb electric field, does not talk to this path at all. That's what happens in linear quantum mechanics. But if I put a second electron next to it, of course, every path of this electron will happily interact with every path of the other electron, right? That's, in fact, how electrons attract each other. We know that very, very well. Now, if you think about this for a second, right? In the path integral formalism, in fact, the paths of the second electron could have really been on top of the paths of the first electron, right? So if you zoom in to somewhere to the middle of any of these paths, how would any of these paths even know which leg they belong to, right? So we are very happy with this part of this path talking to this part of this path. But how does this path know that it actually belongs to this side and not to this side, right? In the middle of the path, you have no idea where this electric field should come from. So why should you think that causality will prevent these paths from talking to each other? Why can't the paths talk to itself? So that brings up the question, why is quantum field theory, which is how we normally use to describe all these kinds of things, why is QFT causal? The reason why QFT is causal is simply because causality is essentially enforced by Green's functions that show up and make sure that, look, if I wiggle this path of the electron, as long as the way that wiggling affects some other path is through a causal Green's function, you know everything is going to be okay. And this brings up an important point. Linear quantum mechanics is basis independent. You can phrase linear quantum mechanics in whatever basis you want. But there's a fact about the world, which is that position is actually special because interactions in the world are position operators. So for example, when I see you sit, I mean, this is how we look at the world, right? When I look at the world, I see you sitting in a location. I don't see you delocalized as some Fourier wave. And that is because even though linear quantum mechanics is basis independent, interactions pick a basis. Interactions care about position because locality is how we see the world, and locality implies we care about the position basis. So why is the position basis a natural way to describe the world? Because of quantum field theory, right? Because our fields are local. So this is the major departure that we did in our work compared to what was done previously. Because previously, what people often do is that they start with single particle quantum mechanics and they try to generalize that. Now, usually what we do, even in field theory, is that we start with quantum mechanics as an uber structure, and then we try to derive field theory from it. What we're going to do is the opposite. We're going to start with quantum field theory as the basis of the world. Because by starting with quantum field theory, fundamentally, you're automatically baking into it causality. You're going to bake in the position basis as being special. Quantum field theory is, in fact, the natural language for us to describe multi-particle states causally. That's why we do it in the first place. So if your problem with nonlinear quantum mechanics was causality, a more natural starting point is actually field theory. And since field theory at the end of the day is what describes the world, if we are able to put in nonlinear quantum mechanics automatically into field theory, we're done. Okay, so that is the basis of our work, the ideas behind it. And now I'll tell you exactly what we did. So let me pause for a second to see if there are any questions about anything.
So, Surjeet, I just want to know, when you say that you don't want to give up probability, do you mean that you don't want to give up the Born interpretation? Or the Born
good.
rule?
So we can discuss this offline if you want. But so what I would say is that one can derive the Born rule. One does not require that as an extra postulate, even regular quantum mechanics. So I'm not giving up anything. The Born rule can be derived, in fact.
So,
and we will discuss this actually when we talk about some of this measurement business that will show up here.
I see. So you put in some kind of probabilistic interpretation, but is it not? Is not coming as a postulate? Is coming as some kind of natural consequence of your?
Yeah. Well, I would say even in regular quantum mechanics that is true. So we'll have this discussion shortly. Let's wait till then.
Okay.
All right.
Can I ask a quick question?
Yes.
Yeah. So is unitarity not already an issue if you have nonlinear terms in the Schrodinger equation? Is it clear that
You can
unitarity
maintain
is...
unitarity. Everything we do will maintain unitarity.
But are there constraints on what kind of nonlinear terms you can add and still maintain unitarity? Does it not?
Well, I mean, the framework that we write down, which we think is the most sensible one, will always maintain unitarity. I mean, it's certainly possible to add, I'm sure, terms that violate unitarity, but you can maintain unitarity while putting in nonlinearity. So yeah, as you will see, putting in causality already restricts what you can do, and the terms we do that we put in will maintain unitarity.
Okay, thank you.
Sure. All right. So, so this is the outline of the rest of the talk. I'll discuss the framework that we are talking about, which will really start from field theory, and we'll discuss the Schrodinger equation for the one particle situation, talk about causality explicitly, and deal with measurement. Nonlinear quantum mechanics is going to have some very strange effects, very interesting macroscopic effects. So we'll talk about that. That's a part of the talk where you guys will think I'm kind of nuts. But the nutsomeness is really coming from quantum mechanics, not even from my theory. And then we'll talk about constraints and tests of this theory that are currently ongoing. And then we'll talk about some important cosmological aspects that show up in the story, and then I'll conclude. All right, so the framework. So as I said, I'm a field theorist. So let me remind you quickly what we do in quantum field theory. So even in quantum field theory, what we are trying to do is solve the Schrodinger equation, right? So this is the Schrodinger picture of quantum field theory. So we say there are quantum states. The quantum states are, for example, you can create them by taking your field operators, creation and annihilation operators, and acting them on a vacuum through a Fock state kind of story. So you create some quantum states, okay, chi of t. And then there are time-independent operators, which are the fields and their conjugate momenta. And then you construct a Hamiltonian, which is an integral over a Hamiltonian density, okay, of phi and pi, of the field and their conjugate momenta. And even in quantum field theory, you are still just solving the good old Schrodinger equation, I d chi dt equal to h chi. It is just that this h is not the one particle Hamiltonian. It is this complicated quantum field theoretic Hamiltonian. Now, I'm going to do something a little bit different here, which we don't normally do, because normally this is useless, but for us, it will be useful. So I'm going to derive this Schrodinger equation from this action. So this action is not the usual action of quantum field theory. This is an auxiliary action that I made up. So here's what I'm saying, right? Imagine there is some path in Hilbert space, not in physical space, but in Hilbert space, where I start with one value of the quantum state chi, and I want to go to a different value of the quantum state chi. And I say, look, the correct theory of the world is one where the correct path in Hilbert space that I'm taking is the path of minimum action of this particular action. All right. So this is just a simple thing that I'm doing. You can quickly verify that if I perform the Euler-Lagrange procedure on this action, I will end up reproducing the Schrodinger equation. So this action is useless in regular quantum field theory because it doesn't add anything beyond what you already know, which is that the Schrodinger equation is how the states actually evolve. But let's think about this for a second. What does this action look like, specifically for the Yukawa theory, for example? So here is my Hamiltonian. I have the fields phi, psi bar psi, and my Yukawa coupling y. So what does this dummy action that I made look like? Well, it's got this chi dot, right? So these are, by the way, just expectation values. So this is my, row and column or whatever, and I put an operator in here to get the expectation value. So this guy, chi h chi, if I plug in the Hamiltonian density for the Yukawa theory, that now contains a term of the form chi, phi, psi bar psi, chi. Okay, so these are some operators, matrices, and I get a number out of it at the end of the day because, say, this chi is a column and this chi is a row. So I've done my usual row column, row matrix column that gives me a number, right? That's the usual Yukawa theory. And for the last 100 years, we have been taking these kinds of theories and adding higher order terms in the operators. So for example, we have the Yukawa theory, phi psi bar psi. Nobody will bat an eyelid if I add a phi squared over lambda psi bar psi, and so on and so forth. These are all higher dimension terms, and we will happily spend money and time looking for these in experiments, as we should. These are all nonlinear in the operators, but they're linear in the states. I only have one chi appear here, right? There's a chi as a row and a chi as a column, and then I'm just adding more and more operators here in this theory. But looking at the structure, right? You stare at it and you see there is a natural thing you want to do, which is that, look, all I want to get my equations of motion is that somehow I should get a number from a bunch of operators, which are matrices, and a row and a column. So if I've got chi, phi, psi bar psi, chi, that's what I have here, can I now not add a new term, okay, which is this epsilon, this new term that I put in, but instead of putting in chi, phi, psi bar psi, chi, I just put in two more chi's here. So I get a chi, phi, chi, and a chi, psi bar psi, chi. What's wrong with that? This is still a number, right? Chi, phi, chi is an expectation value of the operator. That's still a number that multiplies another number. That's it. Why can I not do this? You can go through the story. It obeys all the standard rules you have. You can protect unitarity if you want. I mean, you will automatically by doing these kinds of things. And now you have a well-defined way of getting equations of motion from this, because all you're going to do is apply the Euler-Lagrange procedure to end up getting the corresponding Schrodinger equation that rule the time evolution. But the key difference here now is that the equations you're now going to derive are nonlinear, not just in the operators, they're also nonlinear in the states. It leads to state-dependent quantum evolution, okay? And I'm going to analyze these theories perturbatively. I'm going to take epsilon to be small, and let's just ask, if this is what the equations of the world were, what goes wrong? Is there anything wrong at all? So let's see how to do this, get a feel for how to do the perturbation theory. So let's just take the Yukawa theory, right? So I have y, phi, psi bar psi. And in the usual quantum mechanics, quantum field theory, I would end up getting phi, psi bar psi times y. That is what is there in the Hamiltonian. But now when I put in my extra state-dependent piece, and I go through the Euler-Lagrange procedure to end up getting the equation of motion for the fermion operator psi, let us say, I now end up getting an extra term, epsilon chi, phi, chi. That is the expectation value of the phi operator in the quantum state chi appears in the Hamiltonian. And I'm going to still just solve a Schrodinger equation, an I d chi dt equal to h chi. It's just that h now contains the state appearing by itself explicitly. How do we think about this perturbatively? Well, at zeroth order, this is just regular quantum field theory. So given a quantum state of phi and psi or whatever, just do regular quantum field theory to calculate what chi will be. Zeroth order, there's no problem. At first order, when I want to compute the first nonlinear correction, okay, or to order epsilon, what do? I simply use the zeroth order solution to calculate chi, okay, and then I'll plug that in. That's just a something that I calculate at zeroth order. So at first order, I don't have to know anything at all about the first order correction to chi, right, yet. So I just simply plug that in to compute what the first order correction to chi would be. Now, if you think about it, this first order correction simply appears as a background field in quantum field theory, right? Because chi has been computed to lowest order. I already know what it is. I simply plug that in. That's just now simply a background classical field. So to compute the first order correction that the nonlinearity is introducing, all I'm going to be doing is performing standard quantum field theory calculations on this background field. The only point being that the background itself is determined by the zeroth order quantum state itself. And that's how I compute the first order correction. And this, of course, applies to all orders, because if I want to compute to order epsilon squared, epsilon to the n, whatever it is, I only need to know the state chi to a previous order. And once I've computed the state chi to a previous order, when I want to compute the next order in perturbation theory, this will simply appear as a background classical field. So I'm always able to do this to all orders in perturbation theory. Okay. So now comes the key question. Why is this theory automatically causal? The reason why the theory is automatically causal is because if you look at how the nonlinear terms are appearing, they're appearing only via these expectation values. Now, the key point is this, right? The expectation value of a field operator is an observable of quantum field theory in regular quantum field theory. And observables in regular quantum field theory are automatically causal. So if you think about it, right? At lowest order, in my theory, what's going on, everything is just regular quantum field theory. I'm not even doing anything at all. So at lowest order, this expectation value is going to be causal. Now, when I'm trying to compute the first order correction, of course, the way the first order correction is entering into my quantum field theory is in fact through this background classical field, which is automatically causal, which means the first order correction will also be causal. And then you can go and do this ad infinitum, okay? So explicitly, we can kind of see how this works out. For example, with the example of the particle on the Earth and the particle on Mars. Okay, let's explicitly see why. So what does it look like, right? What does that actually look like? So let's just see the single particle wave function, and then I'll tell you what the two particle wave function is. And you will immediately see why the story is always going to be causal. Okay, let me check the time. Sometimes I tend to blab for too long. Oh God, I've talked quite a lot. All right, so let me speed up a little bit. All right, so for a single particle, how does it actually evolve, right? Now, as we said, if I want to understand how a single particle is evolving due to this nonlinearity, I'm just going to do perturbation theory. So to zeroth order, what happens? I have given you, let's say, a fermion psi, and it just sources the phi field. So I can just simply compute this expectation value chi phi chi. It's a straightforward computation of the expectation value. So what does it look like? Well, you should think about this. I have a single particle psi. The single particle psi is sourcing this phi field. So what is the expectation value of this phi field in the state of psi? Well, that is just simply obtained by computing, thinking of psi, you know, there's a wave function for psi. There is some charge density, if you will, for the psi. And via a Green's function, that will tell you what the phi field will look like. Right? That's just what this expectation value looks like. I just do integral psi star psi times some Green's function. That will tell me what this expectation value looks like. And remember, the causal Green's function is baked in the story. So the key point now is that you realize that the single particle equation that you're deriving really depends upon which quantum field theory you started from. So the Yukawa theory would give you this, psi star psi times the Green's function. The phi-4 theory will give you something very different. Right? This is a very much a field theory dependent change to how the single particle equation looks like, right? But it will do what you expect it to do. If I take a single particle and I, you know, take for example the hydrogen atom story. If I take my proton and I hammer the proton to a point, and I have an electron cloud going around it, and the electron cloud was interacting non-linearly through electromagnetism, let us say, in this particular way, then in fact, if you take this particular theory and you compute the correction to the hydrogen's energy, there will now be a self-interaction of the wave function that will break the degeneracy of the 2s and the 2p levels, okay? And so you can verify those things. And in fact, you can, given the structure, you can prove various aspects of the story that this is a Hermitian form of the Hamiltonian. And because there's a Hermitian form of the Hamiltonian, you have a conserved norm, you're able to maintain probabilistic interpretation. You can also show that because this is a Hermitian evolution, you also maintain unitarity, things of this kind. But let's now get to causality explicitly and talk about entangled systems, right? So how does a multi-particle system evolve when I have this particular thing? The key point here is the following, right? I have my particle on the Earth and I have a particle in Mars. How are these particles talking to each other? They're talking to each other via the phi field, right? That's how they're interacting. If you look at this particular theory, there's an expectation value of chi phi chi in there. So let me take my system on the, I create this entangled system. One is on the Earth, the other is on Mars. And let me now shake the guy on Earth. Well, how is the guy on Earth going to talk to the guy in Mars? He's going to do that because this phi field has to go from the Earth to Mars in order to affect what's going on Mars. But the evolution of phi from Earth to Mars is causal, guaranteed to you by quantum field theory. And thus you realize that, this business of nonlinear interaction is automatically going to be causal because the way different particles are talking to each other is always via these expectation values. And these expectation values are guaranteed to be causal, okay? And it turns out that when Polchinski was kind of thinking about, well, how could there ever be nonlinear causal theories, what he was thinking about is basically, well, if I had these single particle systems, how do I generalize their interaction with these multi-particle states? How do I think about that? So he suggested that the way you could actually have causal nonlinear multi-particle systems was through some sort of additive structure in their nonlinearities. So if you think about it, Weinberg was thinking about psi square and psi star square. Those are multiplicative, you're squaring something. While Polchinski said, look, multiplication would be bad for the reasons that he wrote down, but if there was some kind of additive structure, it would actually be okay. And what we see is that the additive form that Polchinski demanded from very general grounds of causality is automatic in quantum field theory, because that's exactly how this works. That how do I affect something on Mars? Well, I have to first change what's going on Earth, and then it causally propagates, and things are adding up that particular way. Okay, so that, it shouldn't surprise you, because Polchinski's argument was general, and now you see there is a causal reason from field theory why that's actually what shows up.
So can I please interrupt and ask a question?
Yes. Yes.
So in your methodology, it doesn't seem that you have a Heisenberg-like picture, right?
You can go from Schrodinger to Heisenberg easily because of the fact that the theory is unitary. So as long as the theory is unitary, you're actually able to switch from one picture to another. It's just that the Schrodinger picture is the most natural way that I thought about it. So that's why I like talking about it that way.
Yeah, but the unitary evolution will depend on the full state. So my problem is as follows. So suppose we can probably like access measurements only on some past light cone or a future light cone. And then will this theory be predictive for an observer who is just for set up for something that is, say, in a causal domain or in a causal diamond? Is there some?
Yeah. So given an initial condition, this theory solves the Cauchy problem. So that is, given an initial state, you can time evolve it forward. Okay.
Yeah, I understand. But suppose if you are in a certain causal diamond, you cannot, like in usual quantum field theory, you could probably measure only within that, and you can do some predictive, at least some partial predictive thing. But here you need to know the full state on the entire Cauchy slides, right? So
you do.
You do. So here it seems that that this kind of limited predictability is hard. I mean, this.
Well, no. So actually, there are two issues. Okay, it'll turn out there is some very interesting cosmological sensitivity that will come out a little later, but that's not what you're saying. So what you're saying is basically the following: if I have an electron, I have to somehow know the full path of the electron to know what the value of the electromagnetic field is going to be for me to sort of like interact with it, right? There's some element of non-locality in this. But this is no different than what you already have in any system where there are two electrons, right? If I have two electrons, even in regular quantum field theory, if I have to know how the one electron is going to move, I better have to know how the second electron has moved through all its infinite past for me to predict what's going to happen. But the point is, in reality, yes, that's true, but the full path doesn't really matter because the Green's function from very far away is highly damped. So if I had a simple system of this kind, there is no difference in terms of the predictivity of this theory than any other regular quantum field theory.
Yeah, no, but what I was saying is somewhat different, I think. So suppose you have some kind of causal diamond. So in that case, it's like some kind of causal completeness is there, right? Because I have some kind of, if I know a state within a particular patch, I should be able to predict what is the measurement that is this point. I don't need to know.
Exactly, yeah, and that's still what you need here as well.
Whether I can predict from here, although you're right, it is causal, there isn't valid causality, but can I still predict from here what's going to
happen? You can.
Just only this line, whether I can still predict what's happening here.
You can. Okay, I'll be a little bit more cautious about the statement. So it'll turn out shortly that when you say, when people use the word things like causal diamond, etc., you're often thinking very classically about what those things mean. So let me give you an answer, okay? That it is certainly possible to do these predictions, but quantum mechanics is going to make those things a little bit more complicated. So let me defer this response to your question till the end of my talk.
Okay.
Yeah, I want to be careful about what I'm saying. Let's talk about measurement, okay? Now, despite what you've been taught in your undergraduate curriculum, measurement is not some mysterious process. What happens when you make measurements? Well, measurement is nothing but an interaction between a quantum state and a measuring device. So for example, if you want to measure a spin, there is a spin that's in some direction, and you bring it in contact with a measuring device, and you decide what the Hamiltonian is between this spin and this measuring device. You engineer that. And the way you engineer that, you basically say, look, if I have this spin coming to this measuring device, then the Schrodinger equation predicts that the outcome of this interaction between this system and this system is that you get this rather complicated quantum mechanical state where the spin is up and the measuring device goes this direction with the coefficient alpha, plus spin is down with the coefficient beta, and the measuring device does that. Okay. So what I'm saying is the following. Measurement is nothing but me taking a measuring device and a quantum system that I want to measure. I bring these two guys in contact with each other, and then I do time evolution as prescribed to me by the Schrodinger equation. And the Schrodinger equation creates a complicated entangled state as the outcome. Okay. Now this gets a stupid name for some reason. It's called the many worlds interpretation of quantum mechanics. This is actually not an interpretation of quantum mechanics. It's a prediction of the theory. This is what happens when you bring two systems in contact with each other. Okay. The fact of the matter is, in linear quantum mechanics, this becomes all controversial, etc., because it's hard to prove this is exactly what happens for very good reasons. But here is the bottom line, right? You bring these two things in contact with each other, you get this very, very complicated quantum state. And this system, your measuring device, is entangled with a huge macroscopic environment. And because it's entangled with a huge macroscopic environment, you are unable to recover the quantum coherence in the system, which means if you are going to simply understand and describe what happens to the spin alone and not to the full quantum system, which you're unable to access, all of the subsequent physics of the spin will basically look like that of the usual collapse of the wave function picture. Like, in other words, I'm only going to be looking at the spin only, which means I'm only looking at the reduced density matrix of the system. And that reduced density matrix of the system is precisely this quantity, in which case you can think of this quantity as a sum of different worlds, if you will, or collapsed wave functions. Okay, so this is just a statement about quantum mechanics. Now, it is a fact of life that this is not how quantum mechanics is unfortunately taught in our undergraduate curriculum. So many people in the community are confused, and you very legitimately might be confused, and I'm happy to talk about it. But to move on with the talk, this is what I'm going to go forward, right? That measurement is nothing different from just interaction between a quantum mechanical system and a measuring device. All right. So what happens in nonlinear quantum mechanics? Is something bizarre happen? No. Measurement is still the interaction between a quantum state and a measuring device. So I do exactly that. I bring a measuring device in contact with a quantum mechanical system, and and then let the time evolution happen, right? So the time evolution will predict that I end up getting a combination of final states, which I will then interpret as being in a superposition, a macroscopic superposition of many quote-unquote worlds where these things happen. There is one important difference between measurement in linear quantum mechanics and nonlinear quantum mechanics, which is that in linear quantum mechanics, to make a measurement device that is very good, I just need to know the basis vectors of the quantum state and the basis vectors of the measuring device, right? I just need to know that. And then the Hamiltonian doesn't care at all about what the state actually is. As long as I know the basis vectors, I can design and engineer a nice measuring device that gives me whatever outcome I want. But in nonlinear quantum mechanics, the Hamiltonian itself depends upon the unknown quantum state. And because the Hamiltonian itself depends upon the unknown quantum state, it is hard to come up with a perfect measuring device. So what is a perfect measuring device? A perfect measuring device is the following, right? I have some basis vectors for my quantum state, let's say I and J, and I have some basis vectors for my measuring device, let's say AI and AJ. If I know I and J and AI and AJ, and that's all I know, in linear quantum mechanics, I can design a Hamiltonian where when I create this complicated superposition sum of I and AI, I can pick AI and AJ to be orthogonal to each other. I can do that trivially. In nonlinear quantum mechanics, I can't do that. I can't guarantee that because the Hamiltonian itself depends upon the unknown quantum state. It depends upon the alpha and beta, the things that I don't know, which means I can't guarantee a perfect measuring device. So when I do this measurement, I'll end up getting what I get in linear quantum mechanics, but at order epsilon, I'll end up getting some cross terms where I would really be in a quantum state I, but I actually end up getting this other state AJ mixed in as well. So this is some kind of measurement noise, if you will, because the system is interacting with itself. Okay. So these ideas can be straightforwardly generalized, not just to Yukawa theories. You can also go from there to any kind of gauge theory you want, gravitation as well as electromagnetism. These theories are more naturally formulated in the path integral formalism rather than the Schrodinger picture. And you can easily do that. So really what you do is you take your path integral, and to the path integral, you add these chi, a mu chi kind of things. These are just state-dependent terms that appear in your path integral, and they simply, as far as the path integral is concerned, appear as background classical fields. So you know how to do the integral. Same with gravitation as well. You simply add expectation values of the metric, which is also a tensor, in your path integral. And this just allows you to do state-dependent evolution of the theory. And you can make it gauge invariant and stuff like that. So let me pause for a second and ask if there are any questions, because this is the part of the talk where you will really think I'm nuts. But I assure you, all I'm going to be doing is simply computing mathematical consequences of my theory. And the nutsiness here really doesn't even come from nonlinear quantum mechanics. It actually just comes from linear quantum mechanics.
Yes, so I have one question. So it is, when you do this, in the usual case, we can have different field representations, like they give similar answer. The field redefinitions doesn't matter. But here, will it give equivalent theories if I do field redefinitions?
Sorry, field redefinitions.
Field redefinitions, do they give equivalent theories?
Ah, good. So yes, so to paraphrase what you're saying, right, is the following. So we in regular the answer is no. Okay. So at the linear quantum mechanics, right, I could have basically said if I had some field theory, let's say, phi squared, if I have a phi 4 term, I could write that as, phi cubed times phi or whatever, and they all end up giving you the same theories. Here, that's not true. I have to fundamentally say at some level, look, I don't know where quantum field theory comes from. Fundamentally, this field gets this nonlinear term. This field gets this other nonlinear term. So indeed, I'm required at some level to fundamentally state that this operator gets married to this state in this way.
Yeah, but then the question is that we have, so for our knowledge of quantum field theory has told us that we don't have often a very fundamental field, representation. I mean, different field representations, you know, almost surprising. You can even have, say, a non-local field versus a local field.
That is a fact. So see, there's certain things that are nice things that are true about linear quantum field theory, right? So the way I think about it is the following. So if I had a free field, right, a free field has all kinds of symmetries, etc. The moment you put interactions, those don't exist. The free field theory is not going to automatically generate an interacting theory, right? Similarly, linear quantum field theory has a bunch of additional symmetries, okay, and properties, which don't exist in the nonlinear theory. And linear quantum field theory is not going to generate those nonlinear terms. But once you have nonlinear terms, right, it's just like how an interacting theory is different from a free field theory. So I wouldn't say that we know this and that about the world. Yes, it is true that we know certain facts about quantum field theory, which is that quantum field theory, you can basically take your interacting terms and package them in whatever way you want in terms of different operators, right? That's a true statement about linear quantum field theory. We don't know that's true about the world. That's a statement about observations and experiment. And so what I would say is that we don't anyway believe quantum field theory is truly fundamental. We all think there's something beyond it. I don't know what's beyond it. But the point is that at some level, in this particular formulation, I am required to say, yes, this operator is truly phi, and this operator is truly psi. I have to say that. But once I say it, it will then propagate everywhere universally. All right.
Rene has a question, sir.
Yes.
Yeah, hi. So how strong are the experimental bounds on the state-dependent nonlinear modification of quantum mechanics?
We will talk about that shortly.
Okay.
Turns out not very strong, not very strong.
Okay.
Sorry, may I ask a short question just to follow up on what Ayan was asking about field redefinition?
Yes.
So this one is forced on us because of, say, IR divergence will force you to redefine what you mean by a quantum field, right? Say,
certain things are okay. Yeah.
So what's okay?
Yeah. Look, the thing is, right, like you can, so let me be more careful about what I say, right? It's just that in the deep UV, at some point, I have to say this operator, you know, is my phi field and this operator is something else. So think about it that way. At some UV, I pick a bunch of operators and say, this is phi, this is psi, whatever it is. And then you flow to the infrared, right? All of that is perfectly fine. It is just that at some point, I have to say this operator is different from another operator.
Okay, thanks.
Okay. All right, let's talk about macroscopic effects. All right, so let's start with linear quantum mechanics. So let me start with a spin, and a spin, let's say, along the x direction. And let me have an experimentalist, and I have a laser with 2 photodetectors. Okay. Now, the initial state of the world then contains the spin along x, the experimentalist, the laser, and the 2 photodetectors. And I'm going to think about the full quantum state. Okay. My goal is to create a macroscopic superposition. Okay. So I'm not going to create a macroscopic quantum coherent superposition. That is extremely hard to do. I'm going to create a macroscopic incoherent quantum superposition. That's extremely easy to do. So all I'm going to do is measure the spin along the y direction. And depending upon the outcome, I'm going to send the laser along different directions. So let me take spin along x and let me make a measurement along y. When I get measurement of spin up along, say, if I make this measurement, I get spin up and the spin is along the y direction. I'm going to send the laser to the top. If I get spin down, I'm going to send the laser to the right. Okay, that's what I'm going to do. In linear quantum mechanics, there's nothing non-linear about it. When I have done this process of measurement, which is an interaction, quantum field theory, the Schrodinger equation predicts that the final state of the system is that the spin is up along y, and the laser went to the top and entangled with the environment of the laser going to the top, plus down, the spin was measured to be down, the laser went to the right, and the environment is entangled to the right. Right? That's what quantum mechanics predicts. This is quote unquote many worlds because both these states exist. It is not one or the other. They're both simultaneously created. In linear quantum mechanics, we can ask the question, well, which photodetector lights up? We all know the answer to that. When the laser went to the top, this photodetector lights up, and the laser goes to the right, this photodetector lights up. How do you prove that? Well, you can take your linear quantum field theory Hamiltonian, which is epsilon a mu psi bar gamma mu psi, and you can compute various transition matrix elements. When you compute various transition matrix elements, what you will see is that if you're entangled to this state, where the laser went to the top, the transition matrix element of the laser operator, a mu, interacting with the electron over here will vanish. And that is why, formally, when the laser goes to the top, this photodetector does not light up. Okay, nothing deep is being said. This is just how you formally prove this obvious fact. But here is the crucial point. If you take the quantum state chi, remember this is the full quantum state, right? The laser went to the top plus laser going to the bottom, both of them exist. And then if you compute the expectation value of the a mu operator at the point x top and x right, both of these are non-zero in both the environments, in both the quote unquote worlds. And that is because the full quantum state exists. So a mu of x top, let us say, is non-zero for e top, but it is 0 for e right. So when you compute the expectation value, you get no contribution from this state, but you get a contribution from this state. Similarly, a mu of x right is non-zero for e right, but it's 0 for e top. So when you compute the expectation value, you get a contribution from here, but not from there. So in both quote unquote worlds, no matter which part you're entangled in, this expectation value was non-zero. So now you take your Hamiltonian, you then add this term, state-dependent nonlinear term, and you realize the expectation value is non-zero for both these terms. So what happens? When the spin was up, the laser went to the top. At order epsilon, you will now find that this photodetector lights up. Why? Because this expectation value is non-zero. So what is really happening is that the laser from the other quote unquote world that exists simultaneously is interacting with you at order epsilon. This is exactly what you expect from nonlinearity, right? The different branches of wave function are able to talk to each other. Okay, this is called communication between the worlds. And this is extremely interesting because this sort of nonlinearity is visible despite environmental decoherence. All right, I'm not creating a quantum coherent superposition. I'm creating a highly quantum non-coherent superposition. And this is basically what Polchinski wrote down as the Everett phone. Okay, the different branches of the Everett wave function of many worlds or whatever interacting with each other. So that's a consequence of this theory. All right, so let me pause for a second, and that's the craziest thing that I'm going to say. So let me ask if there are any questions.
Surjeet, I want to ask. So now that so you said that okay, I mean this measurement indeed is biased to if you have an ideal measurement, but the fact that when you know that one of these things is definitely up, the density matrix is replaced by a pure state. And that placement of a density matrix, of course, you could say that's very natural, but it's still part of the Born rule, right? In a way. And
no. See, there is a beautiful paper by Goldstone and Coleman, I believe, where without even saying the word Born rule, you can actually derive the entire the entire story just from time evolution. So you can get all of that Born rule measurement stuff simply by time evolving the Schrodinger equation. You don't need anything else.
Yeah. So the follow-up thing that I wanted to ask, the fact that you do not have a very perfect measurement, does it change the fact that you cannot have a perfect Born rule or effectively?
Yeah, I mean, in a sense, it's not okay. It's a question of what you mean by the perfect Born rule, right? So it is true that I don't have a perfect measurement, which means that you'll be like, there is some error. In a sense, you'll be like, look, why is it that my spin is actually up when I go and do measurements, but my experimental device is saying, look, the spin is in the other direction. So it's an error, if you will. So you can call that a deviation from Born's rule if you want, in the sense that there is no direct map between the probabilistic interpretation of Born with what you see in the world. Yes. So yeah, at order epsilon, there is error. That's the correct way of phrasing it.
Okay.
All right. Okay, let me continue. I'm going to go a little over time, but only probably 15 minutes. I'm sorry about that.
It's okay. It's no problem. It's fine.
It's much harder for you guys. It's later in the night there. So yes. All right. Constraints and tests. So now here comes the question, right? You must be like, okay, fine. This guy's talking about all these things. What's the experimental limit on epsilon, right? We have done quantum mechanics experiments for 100 years. So how big is epsilon? How have we constrained it? So let's start with the Lamb shift, right? So what I told you is that, look, the 2s and 2p levels of hydrogen are extremely degenerate. And I told you that if I took a proton and I fix it to a point, and I have the 2s and the 2p levels, the 2s and 2p levels have different charge distributions. One of them is a sphere, the other one is a dumbbell. And the wave functions will interact with each other now because of the expectation of the electromagnetic field. So I will now indeed end up getting a shape-dependent contribution to the energy, the Lamb shift. And we know that the Lamb shift is constrained to 13 digits. So surely the limit on epsilon must be 13 digits or more. But here is something extremely important. And it took us a long time to understand this, and this is a very important point. In linear quantum mechanics, we can decouple the center of mass motion of the atom from its relative coordinates, right? So practically speaking, what does it mean? If I gave you the hydrogen atom, and whether the quantum state of the hydrogen atom is spread over the size of the galaxy, or it is trapped in a little trap, or say a micron-sized trap, and if you ask what is the ionization energy of hydrogen, the answer is the same, 13.6 eV. You don't care how spread out the center of mass wave function of the hydrogen atom is if you're interested in the ionization energy of hydrogen. Mathematically, the reason is because anytime you've solved for the hydrogen spectrum, you go to the center of mass coordinates, and the center of mass coordinates, the relative coordinates, which is what actually tells you the energy levels, decouple from the center of mass motion. So you never care how spread out the hydrogen function is. But that is not true for nonlinearities, okay? Because nonlinearity absolutely cares about psi squared. It cares about psi star psi. So in my specific theory, the way the nonlinearities come in is to the expectation value of the electromagnetic field. So if I take the hydrogen atom and I spread it out over the size of the galaxy, the expectation value is incredibly small versus putting it around in a little trap, right? So the crucial point is the following.
Sorry, may I just interrupt and ask a basic question here? Can you really allow the center of mass coordinates to be unconstrained, like the size of the galaxy, and relative coordinates are unconstrained? That is fine, but can you really have the center of mass coordinates restricted to a small region and have the relative coordinates unconstrained? Because the relative coordinates unconstrained is what how you solve hydrogen atom. If you make that constraint, you'll have to put some appropriate boundary condition at some final.
Exactly, right. So in linear quantum mechanics, you don't have to put a constraint on the relative coordinate at all. It doesn't matter, right? So you're right? Isn't that weird? You'd be like, come on, what is going on, right? Like you'd be like, I constrained the center of mass in this way.
What I'm saying is that if you solve the hydrogen atom in a box, you'll get a different answer from the standard textbook quantum mechanics answer.
Right, because the way you think about the box is that you put the box puts some boundary conditions for you, and you'll basically saying that actually it's a potential on the electron, and the potential of the electron will actually come and change what the actual energy is, right?
Yes, absolutely.
Yeah, I mean, I agree with that, absolutely, right? But what I'm saying is basically let's say I give you a hydrogen wave function, which is some Gaussian. There's no potential on it. And the Gaussian is, say, spread over, let's say, 1 angstrom, say one micron versus the size of the galaxy, right? There's no external potential anymore. And in linear quantum mechanics, the two of them, the ionization energy is still the same.
Right.
Right. Not so in nonlinear quantum mechanics, because in nonlinear quantum mechanics, for the nonlinear terms, I care about the expectation value of some operator in the quantum state. And that absolutely cares how spread out the wave function is, right? So, for example, if I took the hydrogen atom and I localized that to a micron, the expectation value will have one value. If I spread that out of the size of the galaxy, it'll have a completely different value. Now, here comes the important point. People have done a lot of tests for nonlinear quantum mechanics, but they've always done these tests in atomic and nuclear systems, but they've never actually bothered to localize the wave function because it doesn't appear in their head, right? They're not thinking about it that way. So it turns out that all those extreme constraints on linear quantum mechanics that exist from atomic and nuclear physics are useless because they've never bothered to localize the wave function. So for the Lamb shift specifically, two extremely interesting things happen. The hydrogen atom is neutral. So if you actually take the hydrogen atom and you try to do the Lamb shift and you put the hydrogen atom over a micron, 100 nanometer size trap, that's what they normally do, the expectation value is automatically 0. So the constraint doesn't even exist. It's order 1. And for some people have also done Lamb shift experiments with ions. And again, they've never actually bothered to trap the ion to better than 100 nanometer, which basically means all of these effects get suppressed by something like angstrom over 100 nanometer cube, which dramatically decreases the bound from epsilon of being what you might have thought, 10 to the minus 13 to 10 to the minus 2. Okay. So this again similarly kills bounds from nuclear physics because all the QCD effects are going to be localized to a Fermi. But if you take QCD and where do you test it in a nucleus, the nucleus is living in some lattice, and in that lattice, the nuclear wave function is spread over angstrom scales because you run some potential, and that basically means all the QCD effects are completely swamped. So bizarrely, okay, there are no strong constraints on nonlinear quantum mechanics from our study of quantum mechanics in atomic and nuclear systems because nobody has bothered to localize the system sufficiently well. And this is problematic, right? Because the moment you localize, you're putting in a potential, and that potential will come in and mess with your measurement. The leading constraint prior to the experimental work that I'll discuss shortly really comes from accidental things. So we, for example, know that we have been able to trap ions in a lattice. So if the epsilon, let's say, was positive, it would be repulsion. So the Coulomb force of the electron will push itself out. So the fact that we've been able to trap ions in a lattice puts a limit of epsilon of less than 10 to the minus 5. And that's only really true if epsilon is positive. If epsilon is repulsive, this is not true, right? We don't even actually know the bound on that case prior to our experimental work. Now, this does not mean that these things are difficult to test. In fact, they can be tested very easily. And we've actually gotten 3 experiments moving in the last year since we published our paper. So I'll tell you what the experiments are. So the first experiment is basically ion interferometry. You take an ion, you split its wave function into 2 parts spatially. So the same ion goes here, the same ion goes down there. And let's say I have P, probability P of the ion being in this direction and 1 minus P squared on this direction. In linear quantum mechanics, these 2 parts don't talk to each other, even though the ion is electromagnetism, but in nonlinear quantum mechanics, they will. Okay, the Coulomb field of this electron will interact with the Coulomb field of the other electron. And the value of this Coulomb field depends upon P specifically. It depends on the intensity of each of these paths. So if I put half the ion here, half the ion here, the electric field is 1/2 times 1 over r squared. While if it's 90%, it'll be 90% times 1 over r squared and 10% times 1 over r squared, right? So in this particular system, you basically end up getting intensity-dependent phase shifts in the experiment. And that is something that never happens in linear quantum mechanics. And you can use that to combat any kind of electromagnetic background you might basically have. So this experiment was done at Berkeley, and the first round of the experiment didn't find the effect. So epsilon we now know is less than 10 to the minus 11. The other kind of experiment one can actually create is a macroscopic superposition, and talk about how to search for that. So here is how it's happening. This experiment was done at Boston University. So this is like the spin experiment. Okay, I take some quantum spin, I make a measurement of the quantum spin. Let's say I get spin up. So if I get spin up, here's what I'm going to do. I'm going to have a voltage source and a voltmeter. So if it's spin up, I'm going to turn on the voltage source from 10 o'clock to 10:10. And I'm going to turn off the voltage source from 10:10 to 10:20. If I get spin down, I'm going to turn off the voltage source from 10 o'clock to 10:10 and turn it on from 10:10 to 10:20. And I'm going to make a measurement with my voltmeter from 10:10 to 10:20 in the first case, and from 10 o'clock to 10:10 in the second case, right? So in linear quantum mechanics, what's going to happen? From 10 o'clock to 10:10, the voltage source was on, the voltmeter was off. From 10:10 to 10:20, the voltmeter was on, but the voltage source was off. So I'll see nothing at all. And similarly over here, from 10 o'clock to 10:10, the voltage source is off, the voltmeter is on, so I don't see anything. From 10:10 to 10:20, the voltage is on, but the voltmeter is off, so I don't see anything. But in nonlinear quantum mechanics at order epsilon, in this part of the world, I will see that from 10:10 to 10:20, the voltage is reading, voltmeter is reading something, because this voltage source in the parallel world is on, right? That is the communication between the worlds. So again, they didn't find anything. So that again puts a limit of epsilon of around 10 to the minus 11, turns out. Okay, so both of these were experiments that we managed to do with very little resources. So now we're trying to get more money to do more potent experiments. One can do a similar thing for gravitation as well. You take a spin, you make the measurement of the spin, and depending upon the outcome, you put a mass and an accelerometer at different locations. So let's say spin came up, I put a mass, let's say a 1-ton brick at position x1, and at x2, I place an accelerometer, and spin comes down at x1, I place the accelerometer, and at x2, I place a mass. So once again, in linear quantum mechanics, let's say x1 and x2 are far away, this accelerometer won't read very much. But in nonlinear quantum mechanics, because this mass is here at x1 in the parallel world, at order epsilon, I will see its effects. That's basically how you see it. And turns out this kind of experiment is even interesting, even with a null result, which is that formally, we don't really know if gravitation is actually a quantum theory or not, experimentally. Okay, theoretically, we may have our biases. All gravitational experiments we have done so far, we've only solved Einstein's equations classically, right? We take G mu nu and you say G mu nu is equal to expectation value of T mu nu. You've never had to solve the Schrodinger equation to understand how the gravitational field itself responds. So this kind of experiment will actually prove that the gravitational field is capable of being entangled. and you will actually learn that gravitation has non-classical behavior. So we are very interested in doing this experiment, and it's very likely that Fermilab will do this. So this is the last part of my talk, and probably take another 4 minutes. And this is something very bizarre and very important. And this is the cosmological sensitivity, which sort of has a little bit to flavor to some of the questions that Ian was asking at the beginning, but it's a more refined version of it. Okay. So let's think about what's going on, right? Let me think about the experiments that we talked about, right? Where my friend Alex Surshkov at Boston University is going to turn on some electric voltmeter and try to find communication between the worlds and all this kind of stuff. So let's consider the following. Suppose the quantum state of the world is alpha times our universe plus beta times some other universe. Okay. Never in your life have you ever wondered what alpha is. Because in linear quantum mechanics, the value of alpha is irrelevant, right? The Schrodinger equation, I d chi dt equal to h chi, gives you the same answer, whether it is chi or alpha times chi, but alpha could be 10 to the minus 500. So you've never in your life bothered ever what the value of alpha ever is, okay? But now let's think about nonlinear quantum mechanics. So I'm here in this world giving my talk, whatever, and my friend Alex is turning on this electric field. So he's going to compute the expectation value of the electric field, right, in the quantum state. And that's going to give you alpha squared u a mu u, that is our world, and beta squared m a mu m. Now, the key point is this, right? It's only in our world where Alex is doing all these things. Let's say this beta times m could be empty space, right? So quantum mechanics allows you to be in a superposition, but the entire universe, everything we are saying, where I'm sitting and talking, is only a small part of the full quantum state. If you are such a small part of that full quantum state, epsilon could be order 1 big, but alpha could be extremely small, which means the expectation value that I'm creating is incredibly tiny. All right. And that is something about the initial state of the universe. Whoever created the universe may have taken my part of the wave function and made it extremely small. If I've made that part of the wave function to be extremely small, all of the experiments that we are talking about today are going to be useless, because nonlinearity could be order 1 big, but the expectation value cannot be locally changed. The expectation value cannot be locally changed. All of these experiments will give you 0. Okay. So the local exploitability of nonlinear quantum mechanics is determined completely by unchangeable initial conditions. So you still solve the Cauchy problem, okay? But you need to know what the values of alpha and beta are, which is something that you never care about in linear quantum mechanics. It's a huge difference from linear quantum mechanics. And you cannot do anything about it. You can't artificially boost these nonlinear effects, for example, by taking chi a mu chi and say dividing out, which is what we do in linear quantum mechanics all the time. We sort of project out by saying, look, I'm going to go to this specific world that I'm in. But all these projection operators are non-local, right? You can't, there's no local operator for the environment. It doesn't exist. So you cannot even artificially boost nonlinear quantum mechanics, right? Of course, in linear quantum mechanics, we use it all the time, but we don't really need it. Because in linearity, whatever the value of alpha, the answer is the same. So you never care about it. But you can't do this in nonlinear quantum mechanics. And this is, I think, the generic feature of any local nonlinear quantum mechanical theory, in the sense that nonlinearities care about psi squared. They care about the absolute value squared, which means if you are in a system where alpha is small, you can't ever increase it artificially. So what's the interest? We have, many of us believe in inflationary cosmology. And inflationary cosmology predicts that alpha is extremely small, okay? That our universe is a tiny part of the full Hilbert space of the system. So I'm not talking about the multiverse of Susskind and company, okay, where there are laws of the universe being dramatically different in different spatial locations. That could be regarded as hypothetical or speculative or whatever, but this is a prediction of quantum mechanics and inflation, right? Inflation predicts that our part of the universe where we are living and I'm giving this talk is a tiny part of the full wave function of the universe. All right. So in that case, what you learn is that inflationary cosmology is predicting that all of these laboratory experiments of quantum mechanics will tell you that quantum mechanics is observationally linear, right? Because alpha is small. But this does not mean that nonlinear quantum mechanics cannot be tested. That's the interesting fact, which is that inflation tells you that chi phi chi, the expectation of the inflaton or whatever, is homogeneous and isotropic, but it evolves in time. Okay. So what you want to do is you want to think about fields that are homogeneous, but will have non-zero webs in this inflationary state. And there is one state like that, which is the metric. The metric will actually have a non-zero expectation value. It has to. So what this will do is that it will manifest itself as modifications to general relativity. So you take your standard GR metric, let's say around a Schwarzschild black hole or something, -1 minus RS over R, dt squared, whatever. And then that is the metric next to a planet or a star or whatever it is in our world. And now I add to it at order epsilon, the expectation value of the average metric, and the average metric is just Minkowski, right? That's what we expect it to be. So the true metric that a system will actually see is the sum of these two things. And here's the crazy part. When you sum these two things up and you do the standard renormalization to reabsorb, the unknown value of the Schwarzschild mass, etc., it turns out that this metric interference that we're talking about will manifest itself at order RS over R squared. So you take this metric, you take this metric, you add them together, you renormalize RS by swallowing up one value of epsilon. The effective metric that a particle will move in will now turn out to be -1 as RS over R dt squared, that's a standard Schwarzschild metric, plus 1 plus RS over R, that's a standard GR correction to the standard metric, plus at order RS over R squared, there is the 1 plus epsilon term showing up here. So this shows up as a long distance modification of gravity. It corrects the second order GR term, and therefore it is tested only in strong field tests of general relativity. Okay, not solar system tests, any of those things, because you need to have RS over R to be large. And we are just beginning to do this in experiments like LIGO. So that's extremely interesting because we actually predict that there will be deviations in the strong field of GR. So with that, I don't have time to talk too much about the black hole business, but I can talk about it a little bit if you have questions. So with that, let me actually conclude. Sorry for going over time. What we have seen is that quantum field theory can be generalized to include nonlinear state-dependent evolution. There is no causal problem at all to do this. Conventional tests of quantum mechanics in atomic and nuclear systems do not probe causal nonlinear quantum mechanics precisely because they've never bothered to localize the wave functions. But there are actually straightforward set of experimental tests that are possible to probe nonlinear quantum mechanics. Many of them are actually ongoing. And this extraordinary cosmological sensitivity, which is completely surprising, but a very, very important part of the story, tells you that we actually have to think about cosmology and stuff like this as ways to probe nonlinear quantum mechanics. And that's part of what David Kaplan and I have been doing for the last year. So with that, let me actually stop, and I'm happy to answer questions if there are any more.
Thanks, Surjeet, for this really stimulating talk. And so it's time for questions. So please ask.
Yeah.
Yeah, please unmute and ask.
Hello, am I audible?
Yes.
Yeah. Could you please go to the slide where you had this measurement theory part, no?
Sure.
The first one of the measurement theory slides.
Sure.
Where you talk about many words.
Yes, this one. Yes.
Yeah. Well, whatever you were saying, there was a lot of problem with that. So in standard quantum mechanics or the standard von Neumann measurement theory is exactly the same, whatever you described, and it is taught in schools. It's not the case that only many world theory has this or whatever. And at the end of a measurement interaction, what von Neumann, this impulsive measurement model says is that you have a superposition of this multiple joint states of the measurement apparatus and the system, right?
Correct.
The collapse, the question about the collapse is that from this superposition state, how do you ever get a mixed state for the whole system, right?
You don't.
That's what the standard interpretation says, that something magic called as collapse happens and you get this mixed state.
So what I'm telling you is that collapse is wrong, right? It's just not true. We teach it that way. We confuse the people for no reason to do this. It's just that many worlds is psychologically very upsetting to many people. But
in many words, does not solve that either. It just says that different whatever different superposition components are there, they are all in just different words which are originally said to be inaccessible to you. They would be accessible if and only if, like you have said here in your model, there is some crosstalk between these different words. Now you have introduced a crosstalk. That's the only modification. Now, historically, nonlinear quantum mechanics, it was understood that you have to give up one of the many things, unitarity or causality or some such things. I think it was also apparent that you can do state-dependent modifications somewhere. But each of these modifications were felt, uncomfortable for various reasons. Causality, dropping out causality, or dropping out their Einstein causality, which is that you can't have superluminal signaling, etc. That may be very easy to understand. They seem much more sacred. But I just don't exactly recall for what reason state-dependent modifications were not taken seriously. Interestingly, when people talk about Bell inequality violation and various explanations in that context, there are some hidden variable, non-local hidden variable models. It has been pointed out that it is possible to construct a hidden variable model in which the underlying hidden variable state depends on the measurement apparatus. So this sounds somewhat similar to what you are doing, wherein your interaction Hamiltonian depends on the state, right?
Correct.
So that's the interesting part. But you still get a extra component, and that additional error component, whatever you are saying, additional current term. That term, you are saying it's different from the predictions of standard mechanics, quantum mechanics.
Well, in the sense that, like, the time evolution will give you those terms, and so here's the thing.
No,
right?
which time evolution? The you are talking about the usual linear quantum mechanics case, or your nonlinear quantum mechanics case?
So here's the point, which is that in linear quantum mechanics, if I need to measure, let's say, a spin, all I need to know is that the spin, that quantum system has a basis vector spin up and spin down. And I can engineer a Hamiltonian between those basis vectors and a quantum and a measuring device whose basis vectors also I know.
I'm sorry. That's somewhat confusing and misleading way to put it. What you require is that if you want to do a strong measurement, you are measuring, you want to measure spin in some particular basis, let's say, and you want to introduce a coupling Hamiltonian, right? To the so this Hamiltonian, whatever it is, you say you write a form of Hamiltonian, so it will have a system component which you call SI or something, and you have a apparatus variable QI. Typically, if you want to make strong measurement as opposed to weak measurement, or if you want to do projective measurement as opposed to POVM, you have to take the initial state of the apparatus to be an eigenstate of a canonical conjugate conjugate variables eigenstate.
Yeah,
So,
look, let me just cut to the point. Let me cut to the point. I know all that, right?
Yeah, but
is,
that's not
the point is this.
whatever way you are saying it, that's not the way to say it. That's my
no.
Maybe you let the speaker respond.
Yeah, sure.
Yeah, the point is something very simple I'm saying, which is that to create any measuring device, you need to know, all you need to know is what basis you want to measure in, right? Which is what basis vectors you have. And you need to know the states of your measuring device. Once you know that, you can engineer whatever Hamiltonian you want. You don't need to know the exact details of the measuring state itself. That's the whole point. You don't know it. So you don't know alpha and beta, for example. Since you don't know alpha and beta, you just design, but you don't need to know alpha and beta to design this nice measuring device. In nonlinear quantum mechanics, the point is, if I knew what the state already was, okay, if I was cheating, if I already knew what the state is, I can then create a nice measuring device which will perfectly map that state to that. Okay, but what's the point? I already knew what the state was. So the point I'm making is the fact that in nonlinear quantum mechanics, when I actually don't know what alpha and beta are, I'm unable to create a perfect measuring device where there's this perfect correlation between between what my spin becomes and what the outcome of the and the state of the measuring device. That's all.
So here is the question then. In standard quantum mechanics, whether what you are implementing is a strong implementing in a given case is strong measurement or weak measurement depends on whether the initial state of the apparatus was a eigenstate of the given variable.
It will also be a coherent state. It will also be a coherent state. There's no requirement of that kind, right? It just has to do with, look, you are sitting there and you are designing the Hamiltonian. So if you are happy with the coherent state, which you ought to be, you could use that as well. So there's no requirement that any of these things have to be eigenstate.
Let me put it this way. You have a control over whether you are doing a strong measurement or a weak measurement. First question is, do you make a difference between strong measurement and weak measurement at all in your nonlinear quantum mechanics? Second question is how?
No. Look, none of those things change, right? Because the whole point is this. Measurement is interaction. That's all. And all I am telling you here is the fact that, yeah, it is interaction. And the interaction Hamiltonian is somewhat has a small
your post measurement state is different from whatever is in standard quantum mechanics. This is what you are claiming, right?
Correct.
Yeah, but my question was to engineer a state dependent Hamiltonian.
Anjit, maybe you can also go to some other questions because
yes,
sure. If there are other questions, I waited till the end of the talk because I knew this could take long.
So I would like if somebody else has any question also. Okay. Okay, it doesn't seem to be the case. Okay, maybe I think this the measurement thing is, of course, has been so I think what Surjeet is trying to say probably is that your measurements simply have a noise instead of inherent to the nonlinearity, and you cannot.
Yeah, the nonlinearity doesn't change anything, right? It's like it's just an interaction. That's all measurement always has been, and now you are simply putting in some extra terms in the Hamiltonian, so you get a somewhat different answer than what you got before. That's all.
Okay, I mean, I haven't read your paper. Probably, I think I was just disagreeing it the way you are putting it. Not so much so about what is the content of it. Let's see about the content. Maybe I have to read the paper. But can I ask one more quick question?
Yes.
This nothing to do with interpretation.
Yes.
In the slide where you showed a wave function for the universe and superposition. So superposition in what basis? Alpha and beta in what basis?
So this is of the quantum states, or the quantum fields. Remember, I'm a field theorist, so I would simply say, you mean this one of these things? Yeah, this one, right? So yeah, so we have various electromagnetism, whatever it is, right? So our state of the world is you know, so much of the Higgs, so many photons here, so many photons there, whatever it is, right? So it's the field basis, if you will, Fock states of the fields.
I see. Thanks.
Yeah.
Yeah, that's all. Thanks.
Okay, so, thank you. And so I think we have to practically end it at some point. So thanks, Surjeet, for this wonderful talk again. And so I formally stop recording.